Hello all, I am back and ready for Chapter 5. Chapter 5 is called Applying Newton's Laws. Now in Chapter 5 we're going to look at what we know from Chapter 4. In Chapter 4 we learned a number of different things about dynamics. Dynamics, remember, is the study of what causes a motion, the motion of an object to be what it is and or to change. Right? And we learned that a force is a push or a pull on an object, and that objects often experience more than one force, which means when I'm trying to analyze the motion of an object, I have to look at all the forces being applied to that object in order to determine what its acceleration is going to be. What will be the response of the force, or response of the body to the forces being applied. So we do that using a free body diagram. Okay, that shows us all the forces in all the directions, and we did one-dimensional motion, plus minus, and we did two-dimensional motion where we had 360 degrees of possible direction in a single plane, right, in 2 dimensions. Now, we talked about Newton's 3 laws, right? Newton's first law, law of inertia: object will maintain its state of motion unless acted upon by some external unbalanced force. I usually think of that as a soccer ball. If you don't kick the soccer ball, it's not going to move. Right? It needs an unbalanced external force applied to it in order to move. Newton's second law says F equals ma. Right? The mass of the soccer ball is constant, but the greater the F, the greater the force, the greater will be A. Right? The harder you kick it, the further it's going to go. And Newton's third law says the harder you kick it, the more it's going to hurt. Right? When you kick that ball, it's going to kick you back. Okay, so Newton's 3 laws. And then we talked largely about gravitational forces. We talked about the fact that all objects experience a gravitational force because the planet is pulling down on it. Again, we'll talk about some situations maybe when we're outside of the planet's gravitational pull. Let's say if we're on the moon. And then we used strings or ropes and pulleys, and we said that the force that's being applied through a string is called a force of tension. And it's also going to apply the force. It's going to be kind of the connection between where the force is being pulled or being applied and the object itself. So it's a connector. Now, when we talk about gravitational force near the planet, if I have an object that has been dropped, okay, so this object here, right, is falling through the air, and the only force that's being applied to it is Fg. So if I was to say what is the sum of all the forces acting on that object, again, just think about holding your pen beside you and dropping it to the floor. Right now, if it gets super fast, it'll be air resistance. I'll talk about that in a minute. But between your fingers and the floor where it's going to land, it's going to accelerate because there's only one force acting on it, and that is the planet. So we know that the net force acting on that pen that you're dropping is equal to Fg. Right? If I was going to draw that pen, there's the pen, not a very good pen, and I know that the force that's being applied to it is the planet. And that's it. That's the only force that's being applied to your object. Now, what we haven't really talked about yet was the formula for calculating gravitational force. And to calculate the amount of gravitational force that's being applied to an object, we use the formula Fg equals mg. Okay, so that's our formula that says how much is gravity, right? How much is Fg? Well, Fg is equal to the mass multiplied by some number 9.8. So if I wanted to figure out what the acceleration is, what the gravitational force is being applied to a 50 kilogram box, or we'll just say a 10 kilogram box, right? The 10 kilogram box, I'll just make this a bit smaller here. The 10 kilogram box mass is 10, G is 9.8, and I could say that the gravitational force being applied to that box is 98 newtons. So we can calculate the amount of gravitational force using this amazing formula, right? Amazing because we've all been living with this formula from the day we were born. Right? Gravitational force is always there, and as long as you're on the planet Earth, it's equal to m times 9.8. And why 9.8? Because if I go back to my formula up here, I know F net is the same as ma, and I know that Fg is equal to mg, but m is my mass regardless of what I'm talking about here. So if this is the amount of force, if I'm in free fall, right, let's say I have jumped down from, I don't know, I'm just sitting up on a picnic table, and I jump off the picnic table, or I step off the picnic table, and now the planet starts to pull me down. And the reason why I'm going down is because there's an F net pulling me down, and it's going to accelerate me at 9.8 meters per second squared. And I know that the sum of the forces that are acting on me while I'm falling, right, is gravity. Nothing else is acting on me while I'm falling through the air towards the planet. So those are the two forces. And if I say what is the common factor here on both sides is my mass. And because of that, what will be my acceleration? My acceleration is 9.8 meters per second squared, which means Fg equals mg. Right? My gravitational force, how much is pulling down on me? So if I have a mass of 80 kilograms, then I'm going to have a force pulling me down towards the planet while I'm sitting here at my desk of about 800 newtons. Right? 800 times 9.8. Now, everything that we've done so far, we have ignored air resistance. Okay? Air resistance is really, I mean, sometimes I can ignore air resistance. The only reason I'm ignoring it is because it doesn't affect my answer. Right? If I drop my pen, right, as it's falling towards the ground, the only force acting on it is Fg. There is an F air. It's pushing my pen back up, but it's so small that if I was going to say delta D equals V1 delta T plus a half A delta T squared, I dropped it from rest, V1. I know how far it's going to fall. I don't know, 1.3 meters, and I know the acceleration is 9.8 meters per second squared because that's what it is. Then I could calculate the delta t, the time it's going to take, and if I actually do the calculation and do the experiment, I should get the perfect answer to tell me that my acceleration is 9.8. Right? Why is it 9.8? Because air isn't affecting my motion. Right? There is no air resistance. And the reason why there's no air resistance is simply because if it's me falling off jumping off the picnic table, or my pen falling towards the ground, the reason why there's no air resistance is because air resistance is determined by your speed. Actually, your speed squared. So the more speed you have, right, the greater will be your air resistance in the opposite direction to the direction of gravity. So as gravity's pulling you down, the air is pushing you up. Okay, and it turns out the faster your speed, the greater will be the amount of air resistance in the opposite direction. Okay, now, we're not going to get into, in this course or in the 4U course, we're not really going to get into this at all. Right? We're going to ignore air resistance for just about every question, if not every question in both courses. Right, so, if I look at how an object responds to gravity, if I jump out of an airplane, okay, I was just talking to a staff member who jumps out of airplanes quite often, likes to skydive. Right? When you jump out of an airplane, gravity's pulling you down, and the planet is pushing you up. So here's the person. Oops. There's the person going down because of Fg and being pushed up because of F air resistance. Okay, and those two forces are going to act. Now, the whole time that person is falling, right, this is unchanged. Right? So that means as soon as you jump out of the plane, the F air is close to zero, and the only force acting on you is Fg. But as your speed goes up, right, as your speed goes up here, right, your air resistance climbs, And as your air resistance climbs, it's going to push you back harder and harder until you get to a point as V continues to grow here. As V continues to grow, F air continues to grow. As you get faster and faster, your air resistance gets higher and higher until you get to a point where your velocity makes your F air big enough that it will be equal and opposite to gravity. When you get to that point, right, you're at terminal velocity, right? You're at a point where you cannot get any faster. And depending on how you are heading towards the planet, right, if you're going down that way, you have less air resistance and you can actually get to a faster speed. If you are this person here, you're going to have more air resistance and you won't get to the same large terminal velocity. So you can decide how fast you want to go, right, in a range, right, depending on what configuration your body's in as you head towards the planet, right, head first or flat out, or feet first, right. So recognize that in the time between when you jump out of the plane and you're accelerating at 9.8 meters per second squared, and the time when you get to terminal velocity, which is that maximum speed that you can't get any faster than, right? You can't get any faster because then it would be slowing you down. You'd be actually having more air force than there is gravity force, and hypothetically, you may not ever hit the ground if that was the case, right? And that's obviously not the case. So you would get to a point where you get to maximum speed, and during that time between here, where the acceleration is 9.8, and here, where you're at terminal velocity, in between those, you're going to have an acceleration which is dropping, right? It's starting at 9.8, and then 9.2, 8.4, 7.1, 6.3, 5.1, 3.6, 1.7, 0. You're now at zero acceleration. You've reached terminal velocity, and now these two forces cancel each other out, and you are no longer going to accelerate because F net equals 0. Okay, now, what that's telling me is something about terminal velocity here, and we know that terminal velocity is based upon the cross-sectional area of the object as it's falling. As it moves through the air, how much of the object is being pushed by the air, right? For this person here, there's not a lot of air, not a lot of contact between the body and the air. For this one here, because I'm horizontal, there's a lot more contact, so I will go a lot slower. And as soon as I pop that parachute, I'm now going to slow myself down. Okay, so what we know is that if we're here on Earth, basically everywhere on Earth, the G value is 9.8 meters per second squared. Right? Remember, Fg equals mg. Right, so if I want to calculate the magnitude of gravitational force, right, pulling down on that skydiver, how much is Fg? Well, it's a person's mass times G 9.8. Right, little g is 9.8. It's on your formula sheet, 9.8, and I would think that by the end of next week, you will always remember that little g is 9.8 meters per second squared. Notice it's measured in meters per second squared. Right, little g is called the gravitational acceleration. Now, little g is also called the gravitational field constant, because if I look at what little g is telling me, little g, if I take this formula here, let me just go to my whiteboard. If I know that Fg is equal to m times little g, then what is little g? Little g is equal to the ratio of gravity per mass. And what are the units for gravity? Newtons. And what is my mass? Kilograms. So the units here for g, we sometimes say are in meters per second squared. But really, g is also in newtons per kilogram. Right? Newtons of force applied per kilogram of mass. Now, on Earth, there is 9.8 newtons applied for every kilogram of mass. Right? And because of that, because G is 9.8 newtons per kilogram, when I multiply that by kilograms, mass, I will get an answer in newtons. And that's why G can be a newton per kilogram, right? Even though it also works to be meters per second squared. Now, if I go to the moon and I want to do similar work on the moon, the same thing happens on the moon. The gravitational force pulling me down on the moon is equal to m times little g, right? Where little g is equal to the gravitational force of the moon acting on every mass, on every kilogram of mass. But on the moon, it's only 1.6 newtons per kilogram, not 9.8. Now, if little g here is the same as the rate of acceleration, what that tells me is when I drop an object on the moon, the rate of acceleration of the objects on the moon is 1.6 meters per second squared. It accelerates a lot slower. And if you watch the people on the moon, when they're walking on the moon, they don't walk on the moon. They kind of bounce from step to step, because when they use their foot to lift themselves up like we would on Earth, our foot would connect with the ground. If I lift my right foot to move it forward to make my next step, here on Earth, I'm falling into my right foot. But on the moon, when I use my left foot to move forward, it actually gets me airborne, so my right foot is taking a slow-mo move until it actually hits the ground. All right? So the acceleration on the moon is much, much less. Now, the question becomes, why is it less on the moon than it is on the Earth? Well, let's go back to our note here. If I go back to the reason for this, it gets a little more complicated than Fg equals mg. Now, Fg equals mg works perfectly. It works perfectly here on Earth, and it works perfectly on the moon, except on Earth, little g equals 9.8 on Earth, and little g on the moon is 1.6. And if you were standing on Mars, it would be something different. If you were standing on Venus, it would be something different. If you were standing on the surface of the sun, it might be a little toasty, but it would be something different. So recognize that little g, right, is a number that depends on where you are in the universe. Now, the nice thing about gravity is it's universal. And Newton said, I think that gravity is a universal force that attracts all objects in the universe to all other objects in the universe. That being the case, what determines the size or the magnitude of that gravitational force? Well, he came up with his own idea with Cavendish. They came up with their own idea of how this formula would look. And he said, I think that to determine the gravitational force between any two objects in the universe, okay, let's just ignore that big G for a minute. It's determined by the mass of the two objects, mass 1 and mass 2, where mass 1 could be me and mass 2 is the planet that's pulling me down. Okay? The larger my mass, m1, the bigger Fg. The larger the Earth's, or the planetoid I'm standing on, the larger its mass, the greater is Fg. Notice that r is in here too, and r is the distance between the centers of the objects, the gravitational center of mass. For the planet Earth, it's from a spot that's right at the absolute dead center of the planet, and for me, it's the center of my mass, center of my entire body. If I was to try and figure out if I could put one finger under my whole body and suspend me on one little finger that somebody's holding me up, where would that finger be? That's my center of mass, right? My head would be way off one end, my feet would be way off the other, my arms would be off to the sides. My center of gravity would be determined by that point. So M1 and M2 are the masses, R is the separation distance, and Newton and Cavendish came up with the idea that the force is determined by how big the masses are. More mass means more force, and is inversely proportional to the separation distance, the distance between the center of me and the planet. If R gets bigger, F gets smaller. The further I get from the center of the Earth, the less is my gravitational force. G is the magical number called the universal gravitation constant. Okay, just like pi is 3.14 and it makes all those pi r squareds and 2 pi r's and pi, big G is the same thing. It is a universal constant that works everywhere in the universe to look at the gravitational force between every pair of objects in the universe. Right, so like I said, the implications of this are huge because it means that every object will always be attracted to every other object, and when objects get out into space, if there are multiple objects around them that have large mass, they all are going to affect the motion of that object. Right? Now, if we keep going here, okay, like I said, you could actually calculate the gravitational force between you and, say, your neighbor, right? The person who is sitting beside you, if we were sitting in class, or if you're sitting at the kitchen table and there's somebody across the room doing dishes, or if you're sitting on the couch right now and there's somebody on the couch beside you. You could calculate that gravitational force between yourself and that person using that formula. The value for G, big G, the universal gravitation constant, was determined long after Sir Isaac Newton was alive, right? Because to do this, if I'm trying to figure out how much gravity is pulling me down, I need to know a number of things. Number one, what is this G value? 6.67 times 10 to the minus 11. What is my mass? Well, I can just stand on some scales. It will tell me my mass. I need to know the mass of the Earth. Well, it turns out the mass of the Earth is 5.98 times 10 to the power of 24 kilograms. Again, that number is on your formula sheet, right? And we're not going to get into it. Cavendish came up with a way to determine the mass of the planet, but that's basically the mass of the planet. And then R is the separation distance between you and the center of the planet. And again, if this is the Earth, and this is the center of the Earth, and this is you, here in Hamilton, and how far you are to the center of the Earth, well, this radius between here and you is 6.38 times 10 to the power of 6 meters, if I remember correctly. Let me look at my formula sheet. Yeah, 6.38 times 10 to the 6 meters. So now, I know this number here, me, I know this number here, the planet, and I know this number here, r squared. So if I wanted to calculate my mass, okay, I would say, okay, my gravitational force today is mg, which is, let's just give me a mass of, let's say, 100 kilograms, times 9.8, which is 980 newtons. The other way to calculate my gravitational force would be to use G m1 m2 over r squared, where the G is 6.67 times 10 to the power of negative 11. M1 is me at 100 kilograms. M2 is the planet that's pulling me down, 5.98 times 10 to the power of 24 kilograms, all divided by the distance that I am from the center of the Earth, 6.38 times 10 to the power of 6, quantity squared, and I should get 980 newtons. Right, so which should I use? Well, my answer would be use whichever one is easiest. So if I'm on Earth and I know that little g is 9.8, I'm going to do this because it's a lot easier. If I'm talking about an object like the standing on the moon, where I maybe don't know what little g is, you do know it's 1.6, but if you didn't know what it was, but you knew the mass of the moon and the radius of the moon, you could calculate your gravitational force on the moon. Right? If I was looking at a satellite that was up in space, okay, and again, this is where this becomes useful. here's the planet, here's the satellite out here in space, and I'm trying to get that satellite to go around the planet Earth, I need to know that it's not going to come crashing in because of gravity. So to calculate how much force is pulling down on that, I need to offset the gravitational force by the motion of that satellite. And to do that, I need to know the gravitational force pulling on that satellite. I'm going to do Fg equals G times the mass of the satellite. Let's say it's 240 kilograms, right? That's the mass of the satellite. Times the mass of the Earth, 5.98 times 10 to the 24, divided by how far that is from the center of the Earth. Now, if from here to here is 6.38 times 10 to the 20 times 10 to the 6, and this is 0.10 times 10 to the 6. That's 100 kilometers up. So my R value now is 6.48 times 10 to the 6, because that's how far it is from the satellite to the center of the Earth, squared. I can calculate how much gravity is acting on that satellite, and now I can start to do some calculations to try and figure out how do I keep that satellite in space when that's the amount of gravity acting on it. Okay, it's up there. It's not like there's no gravity acting on it. There is definitely gravity acting on it. I mean, way out here, way out there is the moon, and there's gravity acting on the moon. If there wasn't gravity, the moon would be gone, right? And the satellite's way closer to the moon, so I know there's gravity pulling on that satellite, right? I need to calculate that gravitational force so I can now figure out how to get that satellite into space. Okay, so let's finish this note up. Now, if I know that to calculate Fg, I can use either this formula or this formula. They both give me the same answer. And what are these numbers? Well, these numbers are little m here. So let's say this is calculating the gravitational force acting on me. This is the mass of me. And this is the mass of me, right? They're both representing the mass of me. And m2 is the mass of the Earth or whatever planetoid, whether it's the moon or Mars. Maybe we're going to have people on Mars soon. Maybe we want to know how much gravity is acting on the people on Mars. So there's the mass of Mars, and this is the radius of Mars, and I need to square the radius of Mars. Oh, but if I cancel the m's out here, I'm left with little g is equal to g times the mass of the planetoid, or the celestial body, divided by its radius squared. And that will tell me, for any celestial body in the universe, what will be the value of little g? What will be the gravitational acceleration for objects when they're dropped? And I could do that for the moon. If I put in the mass of the moon here and the radius of the moon here and my gravitational constant, which I know, 6.67 times 10 to the minus 11, I could calculate little g, and it would turn out to be 1.6 newtons per kilogram, or 1.6 meters per second squared. Okay, so let me look at the examples here on page 156 to 158. Okay, if I look at example number 1, it's looking at the gravitational attraction between two people. Again, you can do this while you're sitting at home right now. So to calculate the gravitational acceleration, example 1, that's on page 156. Okay, it's telling me that the mass of person 1, 300 kilograms, that's a sumo wrestler, and person 2 is a gymnast who has a mass of 40 kilograms. And the question is, what is the acceleration, what is the gravitational force of attraction between those two people? So I've got person 1 here with a mass of 300 kgs, and I have person 2 having a mass of 40 kgs. And I know that there is a force of attraction between these two, right? And I know that I can calculate it very quickly and easily Gm1 m2 over r squared. Right? I'm not talking about how much gravity is pulling them down to the planet. I'm asking how much gravity is attracting them to each other. And if you put in your numbers, again, make sure you're trying this on your calculator. 6.67 times 10 to the power of negative 11 times 300 kilograms times 40 kilograms divided by their separation distance. Oh, the question tells me their separation distance is 1.5 meters. From the center of the sumo to the center of the gymnast. And if you put all those numbers into your calculator, you should get a gravitational force of 3.6 times 10 to the negative 7th newtons. Now, even though this is a massive person, right, recognize that this is a very small force, right? Very small force. Again, recognize that the force that's pulling down on that 40 kilogram person, 40 times 9.8, which is about 400 newtons. Right, this is 0.00000000004 newtons. Right, this is 10 to the 9. This is 1,000 a million. This is 1 billion times smaller than the amount of force pulling her down or him down to the planet. So the force of attraction between these objects is very small, which means you don't have to worry about getting sucked over across the couch to the person sitting beside you, because that gravitational force of attraction is very, very small. Okay. Number 2 says, calculate the force of attraction between a 1 kilogram melon and the Earth. Oops. So, example 2. I've got a 1 kilogram melon sitting on the Earth. Right, and Earth is 5.98 times 10 to the 24th kilograms. And the R value here, 6.38 times 10 to the 6 kilograms. And to calculate the gravitational force, I'm going to use Fg is equal to 6.67 times 10 to the negative 10 to the negative 11. That's my value for big G, the universal gravitation constant, times the mass of the melon, times the mass of the planet, divided by the radius of the planet, quantity squared, and I'm getting an answer of, look at this, 9.8 newtons. Right, think, okay, why does that ring a bell? Because I could have just done Fg equals mg, and I know that it's a 1 kilogram melon on Earth. On Earth means 9.8, and I get 9.8 newtons without doing any of this stuff up here. All right, so both work. Both will give you the same answer, but recognize that if it's specifically asking you to determine a gravitational force pulling you down to a planet, then, especially if it's Earth, you know that the gravitational acceleration will be 9.8. Okay, lastly, the third example on page 158. So on 158, they actually have an interesting chart that shows you the gravitational fields constant on different planets. On the Moon, it's 1.6. If you were standing on Mercury and you were falling, it would be 3.6 meters per second squared. On Mars, it's only 3.75 meters per second squared. On Venus, 8.83, and on Earth, 9.8 newtons per kilogram, or 9.8 meters per second squared. So this has implications for people who might be thinking about moving to Mars, because the rate of acceleration on Mars is a lot less, which means the pull of Mars on objects is a lot less. And what's likely to happen is people who aren't using the muscles of their legs that much will will probably tend to atrophy. Their legs will get skinnier, their muscle mass will get smaller and smaller because you don't use it. Again, when you're running and working out at the gym and using your muscles, you build muscle mass. If you don't use those muscles for a while, you lose that muscle mass. If you've ever broken a leg and you've been in a cast, or broken an arm, you've been in a cast, and you take it off, you realize, what happened to my leg? Right? It's shriveled up to nothing. You didn't use those muscles while you were in a cast for 4 or 6, 8 weeks, whatever it was, and now you've got to do some physio to rebuild those muscles again. And again, that will happen to people who go to live on Mars. It also shows you differences between the little g value at different places on the Earth. And if it says if you go to Quito, which is in Ecuador, right at the equator, the value is 9.78 meters per second squared. If you go to Hamilton, it's closer to 9.807 meters per second squared. And if you go up to the North Pole, it's 9.83 meters per second squared. So that means there's a greater gravitational pull when you get to the North Pole than there is at the equator, because holding the Earth in your hand, holding it at the North and South Pole between your hands, if you were to squeeze on the poles and it bulges out at the equator, that's what the Earth actually looks like. It's a little bit bulged at the equator. So when you're at the equator, your R value is a little bit bigger, and because Fg is equal to m1 m2 over r squared, right? If the R value gets bigger at the equator, Fg will be smaller at the equator. That's why the gravitational acceleration at the equator is 9.78. If you're at the North Pole, chatting with Santa, you're closer to the center of the planet, so this number gets a bit smaller, and because it's smaller, Fg gets a bit bigger, so the gravitational pull on you is higher, and the rate of acceleration, if you were to drop an object, drop your pen while you're talking to Santa, it would drop at 9.83 meters per second squared. So even though it averages to 9.8 everywhere on Earth, at a second decimal place, there is a more significant, there's actually a very noticeable difference in the rate of acceleration between the different places, in the amount of gravitational force at the different places. Okay, the last question here says, find the weight of a 100 kilogram rugby player. And again, you're just going to go through the same questions that same formulas that we just did. Again, the answer is on page 158 of your textbook. So I'm going to stop there for today. That's a bit of a long note. I'm going to leave you with these questions here on page 181 to work on using the Fg equals mg and or using Fg equals gm1 m2 over r squared. Or maybe it might be asking you to calculate a value for little g. And again, notice to calculate little g, just take the two formulas that we have for Fg, mg and gm1 m2 over r squared, and cancel the m's out on both sides.